In this example, we look at the bonding in sulfur hexafluoride, or SF6, which is used as a filler gas in tennis balls and used to be used as the filler gas in Nike shoes. Here we have the Lewis diagram for sulfur hexafluoride, showing the octahedral structure of the molecule. Also shown are the 3D molecular models for SF6. The first step is to write the electron configuration for sulfur, which being in group 16 and based on its position in the periodic table, can be written as neon 3s2 3p4, which shows us that there are 6 valence electrons in sulfur. Looking at those valence electrons in greater detail, using an atomic orbital diagram for sulfur, we see that 2 of the valence electrons are in the 3s atomic orbital, and the remaining 4 valence electrons are in the 3p atomic orbitals. Now, in order to create our hybridized orbitals, we should note that the 6 sulfur-fluorine bonds in the molecule are all equivalent and identical in energy. So in order to create those 6 hybridized orbitals, we have to start from 6 atomic orbitals, which are the 3s atomic orbital, all 3 of the 3p atomic orbitals, and 2 of the unoccupied 3d atomic orbitals. And mixing all 6 of these atomic orbitals together gives us 6 sp3d2 hybridized orbitals. It's important to notice that the energy of the 6 sp3d2 hybridized orbitals is slightly higher in energy than the 3p atomic orbitals from which they were formed. And this is simply because the hybridized orbitals are just a weighted average of the 3s, 3p, and 3d orbitals from which they were formed. Also, it's important to remember that the 3 unused and empty 3d atomic orbitals remain unhybridized in the molecule and therefore at the same energy. The 6 valence electrons are simply placed in the atomic orbitals based on from lowest energy to highest energy orbital, so they will be placed in the 6 sp3d2 hybridized orbitals with 1 electron in each hybridized orbital. So, as for the bonding in sulfur hexafluoride, we see that the sulfur-fluorine bonds are formed by combining the 2p atomic orbitals on fluorine with the sp3d2 atomic hybridized orbitals on sulfur, where each fluorine atom is bound to a different sp3d2 hybridized orbital. The notation sp3d2 simply states that the 6 hybridized orbitals are formed from 1 s orbital, 3 p orbitals, and 2 d orbitals. This is an important chart that summarizes the hybridization based on the number of electron groups in a molecule. So we see from this chart that molecules with 2 electron groups, namely molecules with the Vespers class AX2, are all sp hybridized. Molecules with 3 electron groups, so molecules with the Vespers class AX3 and AX2E, are all sp2 hybridized. Molecules with 4 electron groups, namely AX4, AX3E, and AX2E2, are all sp3 hybridized. Molecules with 5 electron groups, namely AX5, AX4E, AX3E2, and AX2E3, are all sp3d hybridized, and molecules with 6 electron groups, which include AX6, AX5E, and AX4E2, are all sp3d2 hybridized. This flowchart summarizes the steps required to determine the bond angles, molecular shape, and hybridization for a molecule. So the first step would be to start with a molecular formula, and we would use this to draw the best Lewis structure for the molecule. And this would include accounting for atoms that are required to obey the octet rule, accounting for formal charges, and resonance if necessary. Next, we would use this to write the Vespers class for the molecule, and this is the form that we use for the Vespers class. And once we know the Vespers class, we can automatically determine the bond angles, the molecular shape, and the hybridization.